Hello, I'm Terry Christensen, a marketing specialist from the Ion Chromatography Sample Prep Business Unit. Today we're going to talk about using ion chromatography with high resolution accurate mass spectroscopy, IC-HRAM for metabolomics. Omics is the study of the proteome and the metabolome, from the genome to transcription, then to proteome, and then metabolomics. And it's used to study potential disease markers, but much like the genome studies, they've had much promise and much excitement, but have not really played through completely. However, metabolomics, it studies all the effects of all of these, and in that case, we have already shown some very amazing disease discovery and biomarkers. So to understand the difference between genome and proteome and metabolomics, we have here an example of the monarch butterfly. It's always going to be a monarch butterfly. That's the genome. But as you can see, it starts out as a caterpillar, and that's the proteome and the metabolome, and then it becomes a beautiful butterfly. Now it has different lifestyles. The caterpillar eats different plants, and the butterfly eats little flowers, or nectar from the flowers, and they fly in as well, whereas the caterpillar stays still. That is definitely the metabolomics. It's expression of the proteome, the diet, and the lifestyle. So what is metabolomics? It's a profiling and the screening of targeted analysis of metabolites in the cell, tissue, organ, or organism. Unlike the genome, it provides an instant snapshot of cellular processes. It reveals change in metabolites from a disease state, a diet, or the phenotype, the body size, or the body weight. It also, though, can be used to look at external agents. For example, exposure to pharmaceuticals, environmental contaminants, or poisons. Challenges in metabolism are very large. First of all, we have complex samples, and the field itself is quite complex. It requires both biologists, chemists, spectroscopists, chromatographers, statisticians, and then it brings it back, the information back to the biologists. Therefore, it often requires academia and industry collaboration. The analytes are very diverse, and they have a very wide concentration range, making it challenging for us analysts. Additionally, many of them are small polar metabolites, which don't separate well with many of the traditional analysis methods. The limit of detection is very important, often requiring very low detection limits. And as well, these are isobaric, requiring separation, meaning that with the mass spec alone, they cannot be identified, and we need a chromatography separation method on the front side. And of course, data handling and analysis managed by Sieve and Tracefinder, MZ Cloud, and lipid search. And of course, always identification of unknowns, and that will continue to be a big issue. Where I see high resolution, accurate mass, IC-HRAM has advantages, of course, is in the small polar metabolites and the limited detection and the isobaric compounds, and that's what we're going to talk about today. But without tools, metabolomics has often been described as looking for a needle in a very large haystack. With the right tools, it's a very large, different colored needle in the haystack. Metabolites have very diverse physical properties, from triglycerides to very polar compounds like organic acids and sugars, and nucleotides, from hydrophobic, of course, to hydrophilic. And it requires different chromatography separation methods, reverse phase and HILIC, and of course, ion chromatography, which we're going to talk about here today. The mass spec ionization can handle both positive and negative analysis. So what are the advantages here? First, let's talk about the chromatography, the Dionex IC systems and products. We have a metal-free flow path that provides a bioinert system. We also have exceptional chromatography selectivity and reproducibility to chromatographically separate isobaric compounds. We also have a patented electrolytic desalting suppressor. This removes the ion suppression commonly happening in many of these samples, reducing therefore the sensitivity. And that suppressor also improves sensitivity by reducing the chemical noise. And the Q Exactive Orbitrap, we're keying it with a high-resolution accurate mass spectrometer. It's a patent technology, has mass accuracy to 1 ppm in full scan, and all ion fragmentation ensures confident compound identification. It has high resolving power up to 140,000 and reduces isobaric misidentification, but still requires a chromatography separation method. We have 2 applications we've developed for this Metabolomics. We have a capillary IC system at 25 microliters per minute on the ICS 4000 HPIC system, coupled with the Q Exactive hybrid quadrupole Orbitrap mass spectrometer. It's a 45-minute analysis, and we used it for our non-targeted metabolomic analysis. Additionally, we developed a higher flow rate application at 380 microliters per minute on the ICS 5000 plus HPIC system, coupled with Q Exactive HF hybrid, and this is a high throughput targeted analysis in 18 minutes. But it can also be used for untargeted as well. Let's talk about the flow diagram. As you can see here on the left is the ICS 5000 HPIC modular IC system. This system can be modified in many different ways for many different applications. And we selected this because of its flexibility as well as its high pressure capabilities. And in the box there shows the modular system inside the box. All of our reagent-free systems, the pump only sees deionized water. So you can see on the top, water flows through the pump, and then it goes to the EG where the mobile phase or eluent is made electrolytically, and then it goes through several traps and a degasser, where the sample then is introduced there in between the guard and the degas module, and separated by ion exchange. You can see the sample comes in as a mixture and then is separated at the end of the column. And then after the column is one of our most important devices. It's our desalting suppressor, and that's what makes it possible to couple it with the mass spec. And in line is our first detector. We're using conductivity detector to both monitor the health of the suppressor. After that, the effluent from the conductivity cell is then coupled with a makeup solution of methanol and acetic acid, or you can just use methanol, and it's introduced into the mass spec. Now, these electrolytic devices require a backflow of fluid to drive the chemistry of the electrolytic devices. So since we're using the effluent to go to the mass spec, we're going to introduce now water to drive those reactions up here in the right-hand corner. So let's talk a little bit of how that patented suppressor works. We have the sample, our eluent or mobile phase coming in at the top, KOH, potassium hydroxide. And let's say for this example, we're going to have Analyte peaks as acetate, succinate, and citrate. They're introduced again through the injection valve and separated on ion exchange column. As they come out of the ion exchange column, they are now potassium salts. Okay, and the mobile phase, of course, is also coming out as hydroxide. So now we introduce the suppressor. What it does is exchanges the cation for hydronium, and the potassium goes to waste, and then the analytes are converted to their acids. Now, for the first detector, the conductivity detector, we get an increased response because acids have a stronger conductivity response than for the analytes. But more importantly, for the mass spec, now we have low concentrations now of acids in water, making it now compatible for mass spec. Now, IC has a broad, unlike other separation methods, IC has a broad coverage for polar metabolites. And here we've circled the analytes that ion chromatography can identify and separate. Here we're showing our first chromatogram. This is an ion chromatography chromatogram. We show 49 peaks that we have identified using our separation method. And here are the metabolite peaks. They're ranging from some inorganic compounds that we normally see, as well as organic acids of importance in the glycolysis and TCA cycle, as well as some nucleotides. Now, we compared ion chromatography as the front-end separation with other separation methods coupled to the same mass spec, so we could have a direct comparison between 3 analytical separation methods. With ion chromatography, we were able to get 11 monophosphate sugar isomers, shown here. And why, if the mass spec has such high resolution, why do we need to have a chromatography separation? Shown here, isobaric means that it has the same mass, but it also means that the mass fragmentations have the same patterns. So we're looking at comparison between peak 9 and peak 10, and as you can see, they have the same MS-MS fragmentation patterns. The only way we can tell that the first one, peak 9, is fructose 6-phosphate and the second one is glucose 6-phosphate is because of retention. Now, I see, again, to demonstrate it has a better separation for polar metabolites. Here we compared, we have showing comparison between CAP-IC and HILIC in the left and the blue, and CAP-IC in the green. And as you can see, about the halfway down on the first column, we have glucose 1-phosphate and glucose 6-phosphate and fructose 6-phosphate, 3 peaks. Whereas right next to it is the HILIC method, and we have 1 peak with a couple of knobs on it. So you could kind of say, well, we have 2 peaks there. Also, we have cis-connotate there, the third line on the right, and transaconnotate. These are commonly separated easily by ion chromatography, but as you can see in the HILIC method, they're only able to identify 1 of the isomers. And this is what we expect from ion chromatography. And we want to bring that technology to the metabolomics. It also has extreme sensitivity. As you can see here, we're getting a 60 ppt concentration peak, and the peaks, we still have great peak shape. Now the concentration, we're actually able to get less than 1 femtomole on column with LODs less than 1 nanomolar. And comparison, what I want you to get off this slide is that we have 11 isomers, mono sugar phosphates with CAP-IC here in the blue, and up on top we compared against reverse phase, and on the bottom on HILIC. So on the top they have 2 to 3 peaks separated. On HILIC we have 3 peaks separated, but of course with CAP-IC we have 11. And so what it means is that if you are seeing many of the sugar phosphates, you may have many others that you're not seeing, and your interpretation and then the biology of what's going on may be misleading. What I also want you to look at is the response. If you can see under CAP-IC, we have an E to the 8 response, whereas with HILIC we have an E to the 5 and the E to the, and reverse phase E to the 6 to E to the 7. So we have about a 10 to 100 times improvement in sensitivity. So the point is that IC has superior resolution and sensitivity to HILIC and reverse phase. Now we compared, using this plot, the compounds we could identify with these separation methods, and again shows that a difference between the 3 separation methods and the advantages of IC. Totally, we were able to identify 66 out of many features. Reverse phase was only able to identify 29, HILIC 38, but IC we were able to get 65 out of the 66. So we found more than twice of many of the polar metabolites. And this is in a real sample. This is an oral cancer cell lysates. We also, of course, I mentioned earlier that we also did the method on a 2mm format, and of course we verified that we still have the same great resolution for these difficult phosphate sugars. So we're able to get 11 monophosphate sugars and 9 diphosphate sugars. Now we also wanted to look for a really robust method. So here we took peak 9 and monitored it through retention time of 150 injections. And what we found was great reproducibility in our monitoring. So we want to propose this method as the method needed for metabolomic researchers because of its robustness. We know that metabolomic researchers may be doing thousands and thousands of samples to find that needle in the haystack. So we want to offer our most robust method here using the 2 millimeter application. So in conclusion, many isobaric metabolites, for example, the difficult sugar phosphates, have identical MS-MS fragmentation patterns. Therefore, chromatography separations are necessary for identification and quantification. And ion chromatography provides an efficient and sensitive separation for these small polar metabolites using our patented technology. IC with high resolution accurate mass spectrometry uses our patented Orbitrap technology. We get a 10 to 100-fold increase in sensitivity. We can resolve many more isomers than reverse phase and HILIC, and it provides a superior and complementary method for small polar metabolites. Thank you.